And 9.4 is asking us to calculate the heat required to form a liquid solution at 1356 K, starting with 1 mole of copper and 1 mole of silver at 298 K. And then the book gives the molar heat of mixing of liquid copper and liquid silver. And my book's old, so it has a little typo, but it should be minus 20,590 times the mole fraction of copper and the mole fraction of silver. Okay. And because we have 1 mole of each, we know that XCU and XAG are both 0.5. Okay, so this problem is asking about the heat required. So that is the change in the enthalpy. And when we talk about this change in enthalpy, the first thing we're going to have to do is we're going to have to start at 298, which we know for both of these elemental compounds is 0, because that's the reference as a solid, but then they have to become liquid, which means that we have to go from 298 up to their melting points, go through a latent heat of melting, so adding the energy for that, and then take the liquid from its melting temperature up to the reaction temperature, or the mixing temperature, which is 1356. Okay, so let's do copper first. In the case of copper, copper's melting temperature is 1356. So that means that for copper, without the mixing, the change in the enthalpy is simply integral from 298 to 1356 times the molar heat capacity of copper dt plus delta H melting of copper, which, using the table from the back of your textbook, turns into the integral from 298 to 1356 of 30.29 minus 10.71 times 10 to the minus 3 T minus 3.22 times 10 to the 5 T to the minus 2 dt. So that's the integral. And then the enthalpy of melting is plus 12970 joule per mole. So this is equal to 21833 plus 12970 is equal to 34803 joule per mole, and we have 1 mole, so we have 32,000 kilojoule or 35,000 kilojoule. Okay, now we'll do silver. In the case of silver, silver melts at 1234, so we'll have to do the integral from 298 to 1234 of the heat isobaric constant, or isobaric molar heat capacity of solid silver dt plus delta H melt of silver, plus the integral from 1, 2, 3, 4 to 1, 3, 5, 6 of the molar heat capacity of liquid silver dt. So writing this out, we get the integral 298, 1, 2, 3, 4, and then the heat capacity is 21.30 plus 8.54 times 10 to the minus 3 times T plus 1.51 times 10 to the 5 T to the minus 2 dt plus the latent heat of melting at the melting temperature, which is 11,090 joule per mole, plus the integral from 1, 2, 3, 4 to 1, 3, 5, 6 times the heat capacity of liquid silver, which is just 30.50 dt. And these together give us 26444 plus 11090 plus 3959, which is equal to 41493 joule per mole times 1 mole. So that gives us the enthalpy to raise the temperature of silver solid to 1356 and transform to liquid. Okay. So the next thing is the excess enthalpy. Excess enthalpy. And that is minus 2590 times 1 minus the mole fraction of silver times the mole fraction of silver, and it's a 1-to-1 ratio, so that is 0.25. 0.5 is equal to minus 5148 joule per mole. But now we have 1 mole of copper and 1 mole of silver, which means we have 2 mole. So that gives us minus 10 to 95 joule, which means that delta H is equal to 34803 plus 41493 minus 10295. Delta H is equal to 6.60 times 10 to the 4 joule. And that is the heat required to form a liquid solution of 1 mole of copper and 1 mole of silver at 1356 K, starting from solid constituents at 298 K.